Okay, good evening, Professor David J. De Los Reyes. Okay, my topic for this session will be a continuation of my long video format discussion on trigonometry, and we are now on lesson number 6. Okay, let's proceed. Lesson number 6, it will still be a problem involving okay, the or using the concept of angles. Okay, the title of the topic for tonight will be Trigonometry, lesson number 6, and the contents will be example problem on Pulleys. This will now be a practical application of angles. Pulleys. Pulleys are actually the one rotating on a machine in which the belt is connected. So actually all our machines are actually related to trigonometry because in the computation of their so-called angular speed or linear speed, it's all trigonometry. Okay, I will try to read the problem. A pulley 14 inches in diameter is driven by a belt. We are given a pulley and connected on the pulley is actually a belt. Like the pulley of the so-called any car. The interconnection of the driving mechanism of the car are actually driven by pulleys, right? And pulley is something like a circular thing that got a groove in which you place the belt, and this pulley will be interconnected to another pulley to drive another part of the engine. So trigonometry is actually very important because in the concepts on how machines operate, okay, it depends on all our knowledge on the so-called concept of trigonometry. Okay, I will try to repeat it. A pulley 14 inches in diameter, the diameter is 14 inches, is driven by a belt. This is the belt. If the pulley is turning at the rate of 112 revolutions per minute, this is the pulley, okay? And if the belt is turning at the rate of, what's the rate? The RPM is actually equal to 112. There will be 112 revolutions per minute. It's not so fast, right? It is just like maybe 112 revolutions per minute. It's just maybe the driving mechanism of the one they are using at the post office to transmit the mails going up a conveyor. No, a platform. Those are actually driven by pulleys, and the speed is not so much, right? It's just a slow drag thing, but it is continuously moving. So people could work on top of the what they call this carrier, which is being driven by a pulley. If the pulley is turning at 112 revolutions per minute, how fast is the belt moving? Oh, the problem is just asking if we try to compute for the speed of the pulley, if it is what they call this running or acting in a straight line, what will be the speed? So the problem is being asked is simply just the linear speed. Okay. 112 revolutions per minute is not so fast, right? Unlike in the speed of the so-called synchronous motor or induction motor, to drive so many equipment at factories, their speeds are actually 1,800, 2,500. It's very fast, right? Like the alternator for a car. The alternator for a car to, what do you call this, to charge the battery, it should run at around maybe 1,800 revolutions per minute. Okay, let's try to bring out the figure for this one. I'll just draw a pulley here, two pulleys, and they are interconnected with the belt. So there could be a motor driving this pulley here. Okay, so as this one rotates, the other pulley rotates, and the other pulley rotates. It might, what do you call this, activate a certain platform in which some parts are actually needed. It is the needed thing on this old industries. Okay, let's try to bring out the figure. First pulley, second pulley, connected by a belt. The diameter of the pulley is 14 inches. And the movement of the pulley at certain RPM is 112. The problem is just asking, okay, what will be the speed of this point here on the pulley? Okay, if we are to compute for the speed of it, come to think of it, there is an annotation over here. Because to solve this problem, we must have to bring out this annotation. The speed of the belt is the same as the linear speed of any point on the circumference of the pulley. To compute for the speed of the pulley, okay, as soon as the pulley, as soon as the belt is on the pulley here, we could say that the speed being as is actually in relation with this angular speed over here. Okay? Because we know the angular speed, it's 112 revolutions per minute. Okay? There is a relation of omega with respect to this radius here to get the angular, for the angular speed to be a certain value. So if the problem is asking for the linear speed, if we know the angular speed of the point, as it passes here, the angular speed of the belt will still be the same as the angular of the point on the circumference of the pulley. That is according to that annotation. So the problem is just to be solved by using this formula here. Like from the previous discussion a while ago, from the past lesson, that is linear speed is equal to angular speed designated by Greek letter omega multiplied by radius. Okay, you got it. The linear speed of any point on the belt is equal to the linear speed of any point on the pulley as it rotates. Because we know the data on the pulley. Okay. Let's try to bring out the solution. Since omega is actually the angular speed, in all computations, omega should be expressed in terms of radians per minute, radians per second, or radians per hour. So we prepare, since the angular speed is not so much, we'll try to bring out angular speed in terms of per second. So if we try to bring out the solution, this would be 112 revolutions per 1 minute. RPM is revolutions per minute, or 112 revolutions per 1 minute times. We are now, this part here is the part of the conversion process. We will convert this revolution to radians, so this should be multiplied by 2 per radians per 1 revolution. 1 complete revolution is 2 per radians, right? This is just a conversion factor. Then we'll try to convert this minute here to seconds. So we'll multiply this by 1 minute per 60 seconds. Okay. This part here is just the part of the conversion factor. This is just the angular speed in terms of revolution per minute. Okay. So try to make some cancellation. Since the operation is actually multiplication, we can cancel something on the numerator and so with the denominator if they are equal. So this revolution here cancel with this revolution, and this minute here cancel with this minute. So what remains on the value of omega will be simply radians per second. Computing the actual value, it should be 112 times 2 pi over 60. That's the numerical equivalent. So using your calculator, this should be 11.72. And the unit after the cancellation, what remains will just be simply radians per second. So the equivalent of 112 revolutions per minute in terms of radians per second is 11.72 radians per second. So if the problem is asking for the linear speed of any of the pulley, And as per annotation, this linear speed of the pulley will be the linear speed of any point as it passes through the pulley. The linear speed of the belt will be equal to the linear speed of any point as it reaches the pulley. So by using that concept, linear speed is omega times r. Omega, we computed it already, 11.72 radians per second. Okay, times. The radius is actually, the diameter is 14 inches, so radius will be diameter over 2. So it will be 7 inches. So the times r will be the value 7 inches. Okay, and we'll try to visualize the speed in terms of feet per second. So we will convert this ends here to feet. So this is part of the conversion factor. Okay, this is just omega times r. Then we will try to convert the linear speed in terms of feet per second. So we could visualize it, how fast is it. So this is multiplied by 1 foot per 12 inches. The operation are all multiplication, so we are free to cancel something on the numerator and denominator, and this inch here cancel with this. So what remains will just be simply feet per second. And if we try to multiply 11.72 times 7 over 12, the linear speed of the belt is 6.83 feet per second. It's not so fast, because 112 revolutions per minute, you know. So the belt might be, what you call this, driving a certain machine, okay, in which the requirement is not so fast. So the linear speed of the belt, okay, will be 6.83 feet per second. 6.83. 6.83, it's almost the height of Kobe Bryant, that is per second. So it's not so fast, because 112 revolutions per minute is not so fast. Okay, that's it, guys. This is just another example of the application of the concept of angles. And the application in real life is, this is with regards to the pulleys. We are using this in real life, pulleys. Okay, and our knowledge on the concept of angles, we use that one. Okay, good evening from Los Angeles, Professor David Jill.